Hello everyone, and welcome once again to the Inorganic Tutors Institute. In today's lecture, we will discuss conditional probabilities. Conditional probability remains one of the key concepts and ideas in probability theory. You encounter this in a lot of calculations you do in your probability course. So come with me as we dive into what conditional probability is and discuss its implication in probability theory and real life situations. So without wasting time, let's view into what conditional probability is. So in many probability situations, additional information is available. Okay, so when you say additional information is available, it means that suppose we are conducting an experiment, okay, and we want to know the outcome of a roll of a die. Now suppose I tell you I had an even number after rolling the die. Then you can better predict if the outcome is a 2 or a 4. Let's say I just tell you I roll a die. Find the probability that I'll get a 2. That will be quite difficult, or that probability will be much smaller. Now, if I tell you that after rolling the die, I had an even number, then it means that the chances of getting a 2 becomes bigger and bigger. So you can better tell if the outcome is a 2 or a 4, because in that case, all values that are not even numbers are taken out of the sample space. Suppose I further tell you that the number that I had is a number less than 4. Then there you are. You can accurately say that then the number is a 2. Because if the number is an even number and the number is less than 4, then definitely it is a 2. So this additional information will better tell you or will better inform you to make accurate predictions. So if you are an actuary or a statistician, you can say with 100% accuracy that this outcome is certainly going to be a 2. And in real life, additional information is readily available. Okay, the data we collect on individuals, the details that we find in everything that we do, all these provide additional information for us to make good predictions. That is why I mentioned earlier that conditional probability forms a very, very key concept in probability theory, because in our daily lives, there is always additional information for us to make better predictions. Okay, if I'm to tell you that predict or determine the probability that it will rain tomorrow, okay, you might struggle a bit. But if I tell you that we are in the month of July and it has rained for the past 3 days, now find the probability that it will rain the next day, then you can better tell that, oh, due to this information that I have, I am 90% sure that it's going to rain. But if I don't give you the information that we are in July, it has rained for this number of days, is this and that, you might struggle determining the probability, because you don't even know which month we are in and how the atmosphere works. In that case, conditional probability helps us to make good predictions by giving us extra information about the experiment that is taking place. And as I said earlier, in real world or in our real life, there's always additional information for us. Okay, that's where conditional probability comes to play to make our predictions better. I believe you can now explain conditional probabilities to your colleagues or to your junior students or junior siblings or whatever. Yes, that is what conditional probability talks about. So this information affects how probabilities are calculated. If I tell you that the outcome is an even number, you won't calculate it the same way as if you don't know that the outcome is an even number. It changes. Because you can't tell me that the probabilities remain the same, whether or not you are told the outcome is an even number. If you are told the outcome is an even number, now you know that it's between 2, 4, and 6. So the chances of getting 2 should be 1/3. Now, if you are not told that the outcome is an even number, then you have 6 numbers that can show up. In that case, the probability becomes 1/6. You see how conditional probabilities affect the way we calculate probabilities? It changes the sample space and it changes the probability that we calculate drastically. So once there is information provided, calculating probabilities changes. Okay. So we are interested in probabilities after some event has already occurred. So in this case, the event that has already occurred is the fact that we have an even number. So we are not told which even number the outcome was, but we are given some information that the outcome is an even number, and that changes how we calculate probability. So we are interested in the probability after we know that the outcome is an even number. So that is the overview of what we mean by conditional probability, on condition that this has happened. What is the probability? On condition that it is an even number. It is different from not being told anything at all. Okay, good. Let's proceed to the next slide. So the key idea is that once an event has occurred, has occurred, say the event that the number is less than 4, or the event that the number is an even number, the event that the number is a prime number. Once this event has occurred, or we are told that this event has occurred, the outcomes that are inconsistent with that event are removed. Outcomes that are inconsistent with that event are removed. When we say inconsistent, we mean if we are told that we have an even number, then in the sample space, which is 1, 2, 3, 4, 5, 6, outcomes that are inconsistent. Okay, we don't need 1, 3, 5 again. They are telling you that the outcome is an even number. So what again are you doing with 1, 3, 5? They can never occur. It's like considering 7, 8, 9. 7, 8, 9, they can't occur. So now that we are told that the outcome is an even number, this 1, 3, 5, they behave like 7, 8, 9, 10. They are useless. We don't use them for anything again. So outcomes inconsistent with the event that has occurred, we take all of them out. Okay, so probabilities are now recalculated using a reduced sample space. So the sample space originally was 1 to 6, but because an event which is even number has already occurred, or we know that the outcome is an even number, we clear these that are inconsistent. Now we create a new sample space, which is 2, 4, 6. It means that the outcome is between one of these 3 numbers. It's not between these 6 numbers anymore. We have reduced the sample space. So these are the outcomes that are consistent that matches the event that has occurred. Okay, so that is the key idea. We reduce the sample space by taking out the ones that are not possible again. Okay, let's say you take a quiz and the lecturer comes and mentions that the highest was 10 out of 20. Okay, so it means talking to yourself, you wouldn't consider values like 11, 12, 15, although they might have been your target before. But now that this event has already occurred, now it is certain that the highest is 10. So you throw away those values, those 11, 12, 14, you throw away all of them. Okay, yes, that's what we mean by outcomes that are inconsistent are taken off. We don't need them again because the highest is 10. Why am I thinking about getting a 15 out of 20 if the maximum is 10? So without this information, you can have probabilities for 15. Okay, my chances of getting 15 are 20%. But now that 10 has already occurred, your chances of 15 over 20 is 0. Okay, good. So that's how it behaves here. And take notice, a very, very key concept in probability. Now, let's look at the formula. We've been talking about, speaking a lot. Now, how do we calculate it? So this is how to calculate conditional probabilities. So we have the formula giving us probability of A, we call it given. Okay, there's a lot I'm going to say here. Please make your notes ready and jot these points down because they are really going to help you in some day. So this bar here is called given. Okay, and we put B here. Now, B is the event that has occurred. Given B. So before that, this notation is called probability of A given B. Okay, probability of A given B. So we are finding the probability of A. Okay, that's what we want. So A might be, find the probability that the outcome is 2. That's A. Outcome is 2. But we have been given an information. So in a scenario that I presented, B here is the probability that the outcome is an even number. So B is an even, or the event of even number. And A here is the event of getting a 2 in the exact scenario I presented. Okay, so note the notation very, very well. P of A given B. Probability of A given B. It's written as a bar, a straight bar. And B is the event that has already occurred. And A is the event that we are looking for. Okay, take note of this. So in my example about the even number and getting a 2, B will be event of even number which has already occurred. So occurred. It has already occurred. Okay, and A is event of getting 2, which we are interested in or finding. This is what we are finding. Okay, So we are finding the event of getting a 2, but we have been given that the outcome is an even number. Okay, sure. So if you are asked, calculate the probability that the outcome is a 2, given that the number rolled was an even number. Calculate the probability of rolling a 2, given that the number that was rolled is an even number. So this is how you write it. Probability of getting a 2, given that the outcome is an even number. And it is always equal to P, A, and B over B. Now let's look at what is going on here. P, A, and B. What does it mean? P, A, and B means that A and B should both occur. A and B should both occur. So A should occur and B should occur. The number should be 2, which is A, and the number should be an even number. Okay, so if you are to find the probability that the outcome is 3, given that the outcome was an even number, it means that A should be 3 and the outcome should be even. Is that possible? That is 0. Because you can't find, or 3 cannot occur and even number cannot also occur all at the same time. You can't have 3 occurring and an even number also occurring for a single row. No, it doesn't happen in real life. So that probability is 0. That's why we clear all of the numbers that do not satisfy or are not consistent with the event that has happened, because they will always give us 0. So we don't really care about them. Okay. So that is A intersection B. It means that A should occur and B should also occur. Now let's come to the denominator. This probability of B. Why is it at the denominator? Now remember, when we were finding the probability of an event, we said it's equal to the number of the event over what? The number of sample space. So seeing B here means that the sample space has been updated. The sample space has been updated. It has been changed. Why has it been updated? Because we now have a new information. When you have a new information, what do you say? Updates, right? So in this case, we update the sample space because we have a new information. When there's another information given, we will update the denominator once again. So the denominator keeps changing to reflect the information that we have. Okay, so in case we have that, hey, the number that is even is also less than 4, it means we will change this denominator to the probability of being an even number and less than 4. Okay, so this probability of B you see down here is replacing the sample space. So we will no longer use 1, 2, 3, 4, 5, 6 because there's an update. We will now use 2, 4, 6 for the denominator. Okay, we no longer use 1 to 6 because there is an update. So I'm doing all this for you to understand why this formula exists, not just to be using them every day without knowing why it happens or why it is that way. In that case, if you go and the question is twisted a little bit, you will find yourself wanting. That's why I'm taking the time to explain to you why we have PA intersection B at the top and why we have PB at the down. PA intersection B is saying the two events should occur. A should occur and B should occur. And we have an additional information. So we should divide it by the new sample space that we have. Okay, good. And we have something here that PB should not be equal to 0. There are situations that PB can be 0. Yes. So if B is the event that the number is greater than 6, you know there's no number greater than 6 on a die. Okay, so probability that the number is greater than 6, you know it will be 0. So we don't want that. We don't want B to be 0. Because if the number is greater than 6, then what again can we do? The thing is from 1 to 6, and you are told that the number is greater than 6. So how again will you do your predictions? Because all you can see is from 1 to 6. And someone comes from behind and tell you, after rolling the die, the person had a number that is more than 6. So you just know there's nothing you can do again. So we don't want probability of B to be 0. And if probability of B is 0, also note that we will divide by 0, which is not mathematically true. Or the mathematicians will come and beat us. That why are we dividing? Why are we quiet and allowing people to divide by 0? It doesn't happen that way. And statistically, I've explained to you that if the probability is 0, then there's no way we can further our studies. There's no way we can make prediction if we are told that the roll of a die resulted in a number greater than 6. What again can you do? It's not possible. So we don't want B to be equal to 0. Okay. Good. Okay, so before we move on to solve some, I have questions for you as usual. What you what you enjoy doing, or your favorite, let me say it that way. But before we start that, I also like to give you these tips. Okay, signals. So conditional probability is not always in a direct way for you to know that the event has occurred. It's not always directly told that, given that the number is an even number. No, it's not always the case. So you can see statement that we know that. So when you say we know that, then you should be thinking about conditional probabilities. So we know that the outcome is an even number. Okay, so this in its form is an information. Okay, you can also see on condition that okay, on condition meaning that it has also happened already. And one of the most important, I don't know why I didn't list it as the first point, is if. Very, very important in the head of the conditional terms, aside maybe the word given. You should be very, very mindful of if. So if the number is even, calculate the probability that the number is 2. If this has happened, calculate the probability of this. If the outcome is a blue ball, calculate the probability that it is marked 3. So you have been given the information that the outcome is a blue ball. So you take note of if. We know that on condition that, and you also have this word of those, okay, of those. For the of those, it is mostly given in the preamble. When we get to total probabilities and Bayes theorem, which is our next lecture, you see this term a lot, of those. So we can have that 60% study mathematics. Of those who study mathematics, 20% study English, or 20% play football. Of those who study mathematics, 20% play football. It means that given that the person studies mathematics, the probability that he plays football is 30%. So take note of this word. It's very practical when we get to total probability and Bayes theorem. Of those. Okay. So he's saying out of. So it means a new sample. You're not talking about everyone. You are talking about a specific group of people or group of individuals. So of the balls colored red, meaning we are only talking about red balls. Don't go and add blue or green, which might be in the bigger sample space. We are just limiting you to red. Of those balls colored red, find a probability that it is marked 3. It means that the sample space here is only red balls. It means that you have been given a condition that the ball is red. Okay, of those balls that are red, calculate the probability that it is marked 3. So it's not talking about all the 3s, but it's talking about the 3s that are in the red balls. Okay, so take note of these signals very, very well. Don't always look for given. Given is not the only word that implies that you have been given an information. If you see, we know that on condition that if of those, okay, these terms imply that there is a condition given. So be sure to think about conditional probabilities in those situations. And that's not all. There are times too there's no signal word or not anything like that. It's just given that the outcome is an even number. So it will just be stated before the main question. So the outcome is an even number. Find the probability that it is 2. Okay, so it's also in a form of given. But that one, it doesn't come with any signal word. So let's say we roll a die. The outcome is an even number. Calculate the probability that we obtain a 2. It means you've been given this information. Okay, so once you have all these words or terms or ideas in mind, conditional probabilities shouldn't be a problem. Okay, so now that you are equipped, let's enter into the realms of problem solving and solve some couple of questions to ensure that you really understand what conditional probability is. So the first question for the day: 2 numbers are selected with replacement from the sets 1 to 10. If the second number selected is a prime number, find the probability that the first number is odd. If the second number selected is a prime number, find the probability that the first number is odd. So probability that the second number is prime, find the probability that the number is odd. So the probability that the first number is odd, first, I'm using F to denote that that's the first number. So the first number is odd if, okay, so the if should come behind after the bar, if this. So if the second number is prime. So the probability we are finding is that the first number is odd. But we have been given a condition if the second number is prime. So this equates to P O F intersection PS divided by PS. So the one that has occurred is what comes down. Okay, that's what forms the sample. Okay, so we have this. Now let's go ahead and calculate each component. So let's start from P O intersection P. So because the selection is with replacement, we apply the concept of independence. We are making two selections which are independent. So what you get from the first one doesn't really matter what you get, or doesn't really affect what you get in the second one. If the first one you had 1, it doesn't mean the second one you go and get 10. You can still get 1. In fact, if you get 2 on the first one, it has nothing to do with what you get in the second one. So these two selections we say are independent. So we can multiply the probabilities like this to get this. Okay. Now the probability of odd, we always know there are 5 odd numbers. And we saw previously that there are 4 prime numbers, which is 2, 3, 5, and 7. So the intersection becomes 20 over 100 or 0.2. Okay, so this is what we get for the numerator. Now let's go on and calculate what we obtain for the denominator, which is the probability of prime. So the probability of a prime number is 4 over 10, which is 0.4. Okay, then finally, probability of odd given prime is 0.2 over 0.4, which is 0.5. Okay, so that is the answer we are obtaining, and that is the correct answer. But before that, I will also want to give you this piece of information. Now we see that the selections are done independently. One doesn't affect the other. In that case, the conditional probability doesn't really play a role. Yes, I wouldn't want you to struggle much with that understanding for now. In the appropriate time, when we dive deeper into total probabilities, Bayes theorem, and the others, you get to know why when the two events are independent, conditional probability doesn't really play a role. But before, let me just give you something small to keep with you. So now we want the probability that you get an odd number, given that the first one we had a prime number. Now in real life, the probability that Okay, so the second one, I had a prime number. Does it have anything to do with what I had in the first one? No. The second number I selected was a prime number. Does it really affect what I had in the first place? No, because there's still 1 to 10 and I can still pick any of them. So getting a prime number in the second one doesn't really play a role here. In that case, if you are to take away the condition, you still get 0.5 or 5 over 10. That's a nice behavior we see when the two events are independent. In that case, the condition that is there doesn't really do anything because that condition wouldn't affect the new event. The event that I had a prime number in the second one doesn't affect my chances or doesn't say anything about what I had in the first one. No, it doesn't affect it. So you get 0.5, 0.5. However, for most questions that will be posed in exam or in real life, when you are to apply conditional probability, it's mostly the case that the two events are dependent or they depend on each other. Not like this one that first outcome doesn't have anything to do with second. That's why for all the two, we will get 0.5, 0.5. So the condition there did nothing. I just intentionally placed this example here to tell you that it's not always the case that the condition has an effect, and it has no effect only when the two events are independent. Okay, good. So I think for the couple of questions coming, there's none that the events are independent, so that you appreciate what conditional probability offers. Now we have this. A card is drawn at random from a standard pack of 52 playing cards. So the cards that we know. It is known that the card drawn is red. So this is a condition. So we clear all the black cards because we know that it is red. So we forget about all the black cards. Okay, good. Find the probability that the card is a face card. So this is what you should write. Probability that the card is a face card, given that it is red. Okay. Although you are asked to find the probability that the card is a face card, but you have a condition up there which you have to apply. You can't just discard that information. You have to apply it. Okay. So we have probability of face and red over probability of red. Okay. Now, okay, let's move. Let's take them one after the other. So probability of face and red. So face and red, you ask yourself how many cards are red and at the same time face cards. So we have the jack. So the red cards are diamonds and the hearts. Okay, so 52, so 26 are red and 26 are black. Okay, good. So for the diamond cards, we have 3 of them that are face: the jack, the queen, and the king. Okay. And for the hearts, we also have the jack, the king, and the queen. So a total of 6 cards are red and at the same time face cards. So 2 jack, 2 queen, and 2 king. So 6 cards are face and red. Face and red. Okay. This one we don't multiply because it's just one selection. We just want a number that is face and red. It's not that we are picking 2 numbers. So don't go and multiply probability of face times probability of red. No. It's just one selection. When it's one selection, you just find the intersection and do the normal division. But if it's 2 selection, first one is face, second one is red. It means multiply probability of face times the probability of red. That's when you are told the first one is face and the second one is red. But this one, we want the cards that are face and red at the same time. Okay, so there are 6 out of a total of 52. Okay, probability of face and red is 6 over 52. Okay, probability of the denominator was red. So probability of red is 26 cards also over 52. So there's a probability of face and red. There's a probability of red. Now we divide the two to get our final answer. Okay. So when doing the division, we have 6 over 52 divided by 26 over 52, which we can simplify to get 3 out of 13. So that is the correct answer. So you see the 52 didn't really play a part. It is the number of face and red over the number of red. Okay, good. So you find the 2 probabilities, then you do the division. Okay, good. Let's move on to the next question. A number is chosen at random from the integers 1 to 20. The number selected is even. That is a condition. The number selected is even. Find the probability that it is a multiple of 4. So we are calculating the probability of multiple of 4 given that the number is even. So this is probability of multiple of 4 and even given that it is even. So you find these individual probabilities and you divide them. Okay, so let's do that. So probability of multiple of 4 and given. So we want the numbers that are multiples of 4 and at the same time they are even numbers. So we have 4. I think all the numbers that are multiple of 4 from 1 to 20 are also even numbers. So we have these guys. Okay, maybe I should change or I should clean this probability because it's not a probability I'm finding. So event of multiple of 4 and even is this, and there are a total of 1, 2, 3, 4, 5. In that case, the probability will be the number of events, which is 5, over the total number of sample space, which is 20, giving us 1 out of 4, or in other words 0.25. Okay, good. So now let's do the denominator, which is probability that it is even. So 1 to 20, we have 10 even numbers and 10 odd numbers. So we have 0.5. Then we finally do the division, which is 0.25 over 0.5. So let me compute that accurately here, and you obtain 0.5. Very, very simple and interesting as well. Let's move on to the next question we have. 2 coins are tossed. At least one head is observed. Find a probability that exactly one head occurred. So we are interested in a probability that exactly one head occurred, given that at least one head occurred. So probability of exactly one, given that at least one head occurred. So this is equal to the probability of the intersection exactly one and at least one over at least one. So simple and direct. Okay, yes. So let's obtain the first one, probability of exactly one and at least one. Okay, so now how does exactly one look like? So we are tossing 2 coins. So the outcome are 4. That is 2 times 2. So we have 4 outcomes when you toss 2 coins. So head, head. First is head, second is head. Head, tail. Tail, head. And finally tail, tail. So 4 outcomes. So sorry, this is the sample space. This is not E. This is the sample space. So this is the sample space, not E. So E, which is exactly 1, will take HT. Remember, exactly 1 head, not 2. And to also take TH. So E has 2 outcomes. Now, at least one means 1 or more heads. So we have HH, HT, and TH. Okay, so what is the intersection? The intersection is HH, HT, and TH. Okay, so the intersection is 2 outcomes, or there are 2 outcomes in the intersection, that is HT and TH, over the sample space, which has 1, 2, 3, 4 outcomes. The probability of E and L, because E and L has 2 elements, that is HT and TH, and the sample space is 4, the probability will be 0.5. Now let's calculate the denominator, which is the probability of at least one head. We saw that at least one had 3 elements, that is HH, HT, and TH. TT is not part because there is no head in it. So this is 3 over the sample space, which is 4. So that is the denominator, or in other words 0.75. So finally, the probability of exactly one head, given that at least one head occurred, is 0.5 over 0.75, which can be correctly computed as 0.6667, or 2 out of 3. Interesting, right? Yes. Just that questions on standalone conditional probabilities don't occur frequently, but conditional probabilities form the core of total probabilities and Bayes' theorem, which forms a greater percentage of general probability concepts. Bayes' theorem, total probability, they form a very, very large proportion of general probability theorems. So if you don't know conditional probabilities, or if you can't identify them, or if you mix them with intersections, then you struggle there and you definitely mess up when you get questions on Bayes' theorem in total probabilities. So as we solve, look at what we are doing, look at how we calculate the denominator, the numerator, look at how we express the formulas, look at how we derive the information from the question, and look at how we determine if this is a conditional situation or not. It's definitely going to help you. So if you are finding this easy, then that is a great thing. If you are not, do well, take your time and master this, and don't say this wouldn't come in my exam because the lecturer won't set questions like this. But remember, you use them in the applications where the questions will actually come from. Okay, good. So I think we have the last question for the day, which looks broad, but I guess is the simplest of all. Let's proceed and finish it off nicely. A product is manufactured by either machine X or Y. 40% of the products are produced by machine X. So let's pause here and let me tell you this. When you hear 40% of the products are produced by machine X, or 40% are of X, or 40% are males, or 40% play football, it means that the probability of X is 0.4. 40% play football, it means that the probability of football is 0.4. 40% study mathematics, it means that the probability of studying mathematics or the probability of getting a mathematics student is 0.4. Or in other words, mathematics students form 40% of the probability of the total population. In that case, the probability of getting a mathematics student is 0.4. Okay, so the probability of the products being produced by machine X is 0.4, meaning that the probability of X is 0.4. And 8% of all products are both defective and produced by machine X. And 8% of all products are both defective and produced by machine X. It means that the probability of defective, and I already told you, and means intersection. So probability of both defective and from X is 0.08 or 8%. This is not a conditional statement. It's saying both defective and produced by X, meaning intersection, defective and X. Okay, defective, and its directly intersection. Okay, good. So we have this information: px equals 0.4 and px, or d and x, which is the same as x and d, is 0.08. So with this information, let's now go to the main agenda for the day. So we are asked, find the probability that it is defective. Okay, before that, we are given a statement here. A product produced by machine X is selected. So we are interested in a product produced by machine X. Or in other words, we are told, or it is conditioned on the fact that the product that we are dealing with is from machine X. So it's not all the products, but products from machine X. Okay, so we want the probability that the product is defective. Fine, this is what we want. But it's not all defectives that we are interested in. We are interested in the defectives, given that they are from X. So we are interested in defectives that are from X. So we are being told that the product is from X. Fine, that's an information. So we should find the probability that it is defective. Okay, so this is the condition. You see how it's sometimes unclear to know that this is a condition. But as I already told you, the signal words, which I didn't present much here, but will still come in play, and situations where they are just stated, they all form part of conditional probabilities. So this can be written as P, D, and X over P, X. We have P, D, and X to be 0.08, and we have Px to be 0.4. So we compute this nicely, 0.08 divided by 0.4, and we nicely obtain 0.2. Okay, that's how nice we can approach this particular question. So that ends our total number of questions for the day, and that ends our discussion on conditional probability. I believe you enjoyed the presentation and the teaching, and I believe you now understand what we mean by conditional probability and can apply it whenever question is being given to you. I hope to see you in the next lecture, which will be on total probabilities. Then we finally move on to the Bayes theorem. Have a great time.